So we have a lot of goals when it comes to polynomial functions. We're going to identify them, recognize characteristics, and eventually use all of the things that are listed in the lesson objective to graph polynomial functions. Now, what is a polynomial? I think we know, but let's go ahead and define it. A polynomial function is in this shape, meaning we have a leading coefficient and a degree, and then the terms get smaller each time. The thing that we need to pay the most attention to, though, is this leading term. This leading term has a degree n, meaning that the largest exponent is the degree, and the a sub n is called the leading coefficient. So what's called the leading term, or the largest exponent, has both the degree of the polynomial and the leading coefficient. So some examples and some non-examples of polynomials. This one's real easy. This is a polynomial of degree 5 because we see that every term has a particular power of x, and then we have a constant at the end. Okay? This is an example of a polynomial. It's just in factored form. This is a polynomial of degree 6. I have to the 4th power and then 1, which makes a total of x to the 6th power. These two, however, are not polynomial functions. What kind of power does this term have for this not polynomial? What kind of power is this? A fraction. We're not allowed to have fraction exponents and it be a polynomial. That's it's a reciprocal function or a square root function. Not reciprocal. This one also is not a polynomial. What's wrong with this exponent? It's negative. So this is a reciprocal function. We can't have negative exponents and we can't have fractional exponents. Those are not polynomials anymore. Do you see the difference between yes polynomials and not polynomials? Great. Now what polynomials make in a graph is they make smooth continuous degree functions. Polynomial functions of degree 2 or higher have graphs that are smooth and continuous. By smooth, we mean that the graphs contain only rounded curves with no sharp corners. And by continuous, we mean that the graph have no breaks and can be drawn without lifting your pencil from the coordinate system. These are smooth and continuous. These are not continuous. Do you see how we have this break right here? That would be called a piecewise function. Do you see how this one has a sharp corner? That is not a polynomial. They must be smooth and they must be continuous. Yes? Oops. When we get into it, the first thing we're going to talk about when it comes to polynomial functions is called end behavior. The end behavior of a polynomial function describes what's happening at the end of the graph. We're going to spend some time talking about end behavior. There are only 4 options for end behavior. And it has everything to do with the leading coefficient and the leading term. Okay? If this term right here, the leading term, is an odd degree function, meaning that the exponent is an odd number. Do you see how these arrows are going in opposite directions? Odd degree is opposite directions. If you have an even degree function, you see how they're both going up or both going down? So even functions, their end behavior goes the same direction. Now, which direction it goes depends everything on the leading term, the leading coefficient. The leading coefficient controls the right side. So I want you right now to highlight all of these right arrows on the graph. Do you see how for when the leading coefficient is a positive number, the right side goes positive, it goes up. If the leading coefficient is negative, the right side goes down. Okay? After you decide what's happening on the right side from the leading coefficient, you just decide if the left side should go in the opposite direction or in the same direction.
So odds are more like they're going to be like either up to the right or down to the left.
So the odds are going to be opposite directions.
They just make like parallel lines basically. But like if you
for looking at that particular graph, I see why you say that. But in general, here's what they're actually going to look like.
I meant like to remember which ones would be even and which ones would be odd, because the evens make like a V.
Sure. Even V. That works. Love it. Let's remember that. What we're going to be wanting to describe here is what's occurring on these different things. So in this first graph, this is going to be an odd degree positive leading coefficient. I know it's a positive leading coefficient because on the right side goes up. But since it's an odd degree, positive means right side goes up. Odd degree means the other side goes opposite. So on the right side we are rising and on the left side we are falling. For the second graph, it's odd degree, odd opposite. But if it's a negative leading coefficient, that means we're falling on the right side. Right side goes down and left side goes up. I don't know what's happening in the middle. We're not talking about middle behavior. We're just talking about the end behavior. The third option is an even degree positive. Again, positive, the right side goes up. But even means that the left side also goes the same direction. So on this one, both of them rise. Our last example is an even degree negative function. So negative means the right side goes down. Even means the left side falls the same way. And all of this is controlled by that leading term, the leading coefficient and the degree. So that concept with your arms, just like we played, will be very helpful for answering these kinds of questions. Example 1 says use the leading coefficient test to determine the end behavior of the graph. Okay, all I need to do is to identify the leading term, and I think there's a typo here. This should be a 4. Oh my goodness. This should be a number 4. Yowza. Okay, which means that our leading term here, our biggest exponent is this guy. Yes? So my leading coefficient, the number in front of x to the 4th power, is greater than 0 because it's the number 1. It's 1x to the 4th power. My degree is even because it's a degree 4 function. So what does your end behavior look like if that's the function? Yeah, I see arms going up in the air. That's right side going up, and even means left side's going up. So we're going to rise on the left and rise on the right. That's how you answer that question. Rises on the left, rises on the right. Okay. What about this one? It's not in standard form, so we have to do a little bit of work to determine the leading coefficient. There's an x cubed here, an x squared here, and an x. So what's the total number of x's if I multiplied all of this out? 6 is correct because it's 3, 4, 5, 6. So I know my degree is going to be even again because it's a degree 6. What would be the leading coefficient? If we were to multiply all of these things out, it would be negative 4 times 1 times 1. Which means negative 4 would be my leading coefficient. It's negative. What would your arms look like if this was the information you had? It would be right side down, left side down, which means we're going to fall on the left and fall on the right. Just because these are notes, you might want to write down to yourself that the leading coefficient or the leading term here is negative 4x to the 6th power. That way when you're looking back at your notes, you know where that all came from. Yeah, because it's 3, 2, and 1. So that's a total of 6. And if I multiply those leading coefficients, that's negative 4 times 1 times 1. Coefficients multiply, exponents add. That's a great question. Yeah, exponents add, coefficients multiply. So like a piece beyond this, kind of going past just doing the arm motions for this, right, is using the leading coefficient test to decide if something is all of the information we need. It says, the graph of f of x is obtained with a graphing utility using a negative 8 by 8 by negative 10 by 10 viewing rectangle, which means it's negative 8 to 8 and negative 10 to 10. That's what we're looking at. The graph is shown in the figure on the right. Is this a complete graph that shows the end behavior of the function? Because right now it looks like the end behavior of this graph is falls on the left, rises on the right. If we do the leading coefficient test though for this function, let's talk about what I should see on the graph. For the one that we have right there, it says negative x to the fourth, which means the leading coefficient is less than 0, and my degree is what? Even. We know that a function that is even degree with a leading coefficient that's less than 0 should have what kind of end behavior? Fall, fall. So does this show me all of the graph itself? No, this is really important because a lot of times when you're dealing with polynomials, they don't actually all show up on your screen and you have to zoom out to see it. If we zoomed out a little bit, you'd actually see that this graph does like this number, something like that. We just cut off this entire side of this polynomial, and so we would have been confused and answered incorrectly. Don't trust the graphs necessarily. Look more at the equation to make sure you're seeing the whole thing. Because we knew this was not the correct end behavior, we know we're missing part of this graph. So the answer here is no. Is this a complete graph? No. End behavior tells you a lot of information about the different types of functions. Okay? When we get into it, if we move on a little bit, we're going to talk about the zeros of a polynomial function, and there's an entire chapter or section in this chapter about the zeros, complex zeros and crazy zeros for polynomials, but we're going to start at the beginning. If f is a polynomial function, the values of x for which f of x is equal to 0 are called the zeros of f. Okay? We also can call these the roots or the solutions, or better yet, the x-intercepts. That's what we're finding when I'm asking you for the zeros. So back in Algebra 1, you probably learned this acronym, the ROCs. The ROCs words are the roots, zeros, x-intercepts, and solutions. They're all the same thing, and it's going to be where the graph crosses the x-axis. But they have different uses, so you'll see me talking about the zeros a lot. I'm talking about the x-intercepts. Now, there's various methods to find the x-intercepts or finding the zeros, especially when we don't have a graph. The first one we're going to start off with is factoring by grouping. So if we're finding all of the zeros of this polynomial function, I see that there are 4 terms. If you have 4 terms, that means in your brain you need to think, all right, I'm going to solve this by grouping, because it doesn't work with the quadratic formula. It doesn't work with anything else that we've learned so far except grouping. Now what grouping is going to do is it's going to have us split the polynomial into 2 parts. So I have the first 2 parts, and I have the second 2 parts. Just visually in your brain, you're separating them into 2 groups. The stuff that I have in pink right there, and yes, it's pink, what do they have in common? They have x squared in common. Well, if I factor out x squared, my leftovers is x plus 3. Yes? What do negative x and negative 3 have in common? They're both negative. So if I take out a negative 1, I end up with x plus 3. Oh, snap. Look at what is in those parentheses now. Yeah, so now I can combine the stuff in the front, x squared minus 1 as one factor, and x plus 3 as the other. But hopefully your spidey senses are tingling, because x squared minus 1 is the difference of 2 squares. What does this automatically factor out to? X minus 1, x plus 1. Once we have our polynomial function in factored form, or as factored as possible, finding the zeros is really easy. There are 3 zeros here. The zeros are 1, negative 1, and negative 3. So we want to get it in factored form or in root form so that we can just very easily find those roots. In example 5, do I have 4 terms again? No, I have 3 terms. When we have 3 terms, there's a strong possibility that you're going to be able to use factoring in some way. You're always going to want to make sure you check the GCF. And then you might get to be able to factor it like a trinomial situation or a quadratic form situation or any of the ways we studied solving quadratics in chapter 1. So what do all 3 of those terms have in common? X squared. We're going to go ahead and make it negative x squared as my GCF because I want my trinomial to have a positive a value. So if I get rid of x squared for everything, it just changes the sign and reduces all of the exponents by a little bit. So I took out x squared. That was the GCF. Now, can we factor that trinomial? Yeah, the numbers that multiply to 4 and add to -4 are -2 and -2. And once it's in fully factored form, you can find the zeros really easily. The zeros for this function are 0 and x equal to 2. Now, a question I'm probably expecting to have is, where did the 0 come from? Yeah, negative x squared. If I set this term equal to 0 and solve, you would get 0 when you took the square root of 0. Now, why did I only write x equal to 2 down once? Yeah, they're the same. If I solved both of these, this would give me x equal to 2 and this would give me x equal to 2. I don't need to list it twice. It's called a repeated root. Okay, these sorts of questions of find the 0, there's going to be a variety of ways that you get through the solving part and the factoring. And if you're stuck, maybe look through chapter 1 notes to see some other ways in which we solve these kinds of questions, because there might be a variety of things you can use here. But as we get more complex with our polynomials, we got to start talking about what's called multiplicity. The multiplicity of a 0 is basically the number of times that a particular function repeats. So a particular, not function, factor. If r is a 0 of even multiplicity, meaning that the k value is even, then the graph touches the axis and turns around at that point r. I like to call that a bounce. Your book calls it a touch and turn. I'm going to call it a bounce. If r is a 0 of odd multiplicity, meaning that the k is an odd number, then the graph actually crosses the x-axis at r. This is going to be helpful because we're going to be able to graph the zeros and decide whether it crosses through the x-axis at that 0 or if it bounces, touch and turn, at that particular 0. But multiplicities are really easy to see because once things are in factored form, we can talk about the multiplicity of each 0. If this is the function that I'm given and I factored it and it looks like this, first of all, what are the zeros that solve this question? -1 and what else? 3/2, because you change the sign of 3, divide by 2. But now let's talk about their multiplicity. How many times is the factor x plus 1 repeated? Once. So it has a multiplicity of 1. And since 1 is an odd number, it's going to cross through the x-axis. How many times is the factor 2x minus 3 repeated? Twice, because it has a power of 2 on the outside. You see this right here? So its multiplicity is 2. Since 2 is an even number, it's going to touch and turn. I'm going to call it a bounce. Your book calls it a touch and turn. I just can't help myself. Bounce is a less words. Touch and turn. So it will bounce off the x-axis at that particular value. Okay, Keep multiplicities in mind for when we start to graph our functions, because it's going to tell us what happens at those zeros, whether it bounces or crosses through. We need 2 more pieces of information in our back pocket before we start trying to graph polynomials. Can we handle 2 more pieces of information? Great. On the next page, we're going to talk about what's called the intermediate value theorem. Sounds really complicated and uses complicated notation, but it's really kind of like a, oh, well, duh, that makes sense. The intermediate value theorem says that if f of a and f of b have opposite signs, then there is at least one value c between a and b for which f of c is equal to 0. Listen, this is a textbook definition for something that's not very complicated. This right here is going to be f of a. Okay, this is f of a. We're at a negative y value, yes? That's f of a. F of b is going to be up here. That's a positive y value, yes? If you go from negative to positive, what do you have to pass on a number line to go from negative to positive? You have to cross through the x-axis. You have to cross 0 to go from a negative number to a positive number, which means there is at least one place in between there where it crosses the x-axis. And like, duh, the only way to go from negatives to positives is to cross through the x-axis. That's all that the intermediate value theorem is telling us, okay? So when we use the intermediate value theorem to prove that there is a 0, it's a lot of writing when it comes to mathematics because it's a theorem that we're proving. It takes 3 steps. 2 information steps and 1 conclusion step. The first information step is to evaluate the function at one of the values. So for me, I'm going to evaluate this yellow function at the blue number. So here we go. I'm evaluating. I'm going to say, all right, step 1, I'm going to find f of 2, which means I take 2 and I plug it in. This is 2 cubed minus 2 times 2 minus 5. 2 cubed is 8. 2 times 2 is 4. We're going to subtract 5. Our output is negative 1. Step 1, we evaluated f of a, f of the first number. We're going to repeat that step but with a different number, f of 3. So we do 3 cubed minus 2 times 3 minus 5, which is 27 minus 6 minus 5, which is 16. Then we compare those numbers. Is one of those numbers negative? Is one of those numbers positive? So we know in between them there has to be a place where our graph crosses 0. So we say the following. We say, since f of 2 is less than 0 and f of 3 is greater than 0, the function has a real 0 between 2 and 3. So again, that's saying that since the first number we evaluate is negative and the second number we evaluate is positive, or vice versa, it could start off positive.
So if they're both positive or both negative, it wouldn't.
Correct. You could not use the intermediate value theorem to prove that there's a real 0. If they change signs, though, that's enough information by the IVT, intermediate value theorem, to prove. And that'll help us graph, because if we know like our x-intercept is negative and our y-intercept is positive, then in between the x and y-intercept, well, x-intercept would be the answer, but if we had 2 coordinate points, we'd be able to see that obviously somewhere there's a 0 in between those 2 values. That's the intermediate value theorem. Let me get these colors to match because I just realized I used different colors. Okay, last piece of information we need before we can really be pretty good about graphing a polynomial function is the theorem that involves the turning points of a polynomial function. Turning points, don't think too hard about it. It's straight up where it turns, goes up to down or down to up. In general, if f is a polynomial function of degree n, then the graph has at most n minus 1 turning points. So if we look at this example that we have here, there are 1, 2, 3, 4 places where this thing turns around. 4 turning points. So if I have 4 turning points, then there's a strong possibility that this thing is degree 5 or more. It can't be 4, it can't be 3, it can't be 2, it can't be 1. If we have 4 turning points, then we know it's degree 5 or higher. That's a great check at the end of graphing a polynomial function to make sure it has the right number of turning points or has the right degree. So we're going to put this all together and create a strategy for graphing these polynomial functions. We've already kind of seen these like steps that we're taking when it came to quadratics today, but we're going to apply that to polynomials. We're almost there. Come on, keep up with me. Step number 1, we're going to do the leading coefficient test, which is looking at the very first term to determine end behavior, so you know where to draw the arrows. Just like we did with quadratics, we're going to find those x-intercepts by setting f of x equal to 0 and solving. If there's an x-intercept, then we're going to check the multiplicity. And for our multiplicity, if k is even, the graph touches and turns or bounces. If k is odd, the graph crosses the x-axis. We will then compute the y-intercept the same way we did with quadratics by computing f of 0. We will then use symmetry to determine if we can plot some points. Since there's no necessarily axis of symmetry, we have to decide if there is symmetry in the graph by checking f of negative x. So let me highlight this for you guys. This is what you're doing to decide if you have symmetry. And last but not least, you're using that turning points idea to make sure that the graph has been drawn correctly. So we've got a lot of pieces of information to put together to be able to graph one polynomial function. Are you ready?
Yeah.
Thank you for your honesty. We're doing it anyways. I know. It's a whole page. Most of you will not need the whole page because you actually have nice, neat handwriting, but use your nice, neat handwriting. Okay, first things first. We're going to take this function and we're going to do the leading coefficient test. Number 1, leading coefficient test. The leading coefficient, is it positive or negative? Positive. And the degree, is it even or odd? Even. All right, so that means by the end, we know that we should have the right side going up, rising, and the left side also rising. Check. Keep that in mind. Step 2. Look, we're already on step 2. Amazing. Step 2 is to find the x-intercepts. We find the x-intercepts by taking the function and setting it equal to 0. So this would be x to the 4th power minus 2x squared plus 1 equal to 0. Are there 4 terms here? No. Can we use grouping? No. Grouping is for 4 terms. So we're going to try to factor this, but oh no. Is this a squared? So is this a regular trinomial that we're used to factoring? No, so we're going to throw it back to something you guys hated in chapter 1. This is a u substitution problem. So what we're going to do is we're going to let u be equal to x squared. And we're going to rewrite this problem. Okay, if I rewrite this problem, it's like we can do x squared squared minus 2 times x squared plus 1. But if we let u equal to x squared, we would just rewrite this as u squared minus 2 squared. I mean, what? 2u squared. What? Not squared. Ugh, 2u equal to 0. Is that, with the u's in it, something that's pretty easy to factor? Yeah, what does this factor out to? Yeah, u minus 1 and u minus 1. Because negative 1 times negative 1 is positive 1. Negative 1 plus negative 1 is negative 2. Now we put everything back, because we've got it factored, but we want it to be back with x's. So we put the x squareds back. Unfortunately, I'm still not done, though, because remember, we're trying to find the x-intercepts. Do you recognize that this is difference of 2 squares twice? Yeah, x plus 1, x minus 1, x plus 1, x minus 1 equal to 0. And like, that looks way chaotic to me. So we can reduce this down to maybe something that's a little bit easier to look at. Here's the thing that might be easier to look at. Isn't this just x plus 1 repeated twice and x minus 1 repeated twice? Which, oh my gosh, means that we have a 0 at x equal to negative 1 and a 0 at x equal to 1. But since this is a polynomial, we have to check multiplicities as well. What's the multiplicity of the solution x equal to negative 1? The multiplicity, remember, is the number of times that that factor is repeated. Twice. So my multiplicity here, oh my gosh, switch colors. I don't know why it's not switching to orange. You get it. My multiplicity here is 2, which means we're going to bounce or touch and turn at the number negative 1. What's the multiplicity of the solution x equal to 1? Also 2, because this is repeated twice, which means there we are also going to bounce. This is good information we need. So far, what we have done is we have found the end behavior. We know that at the end of this graph, it should be rises on the left, rises on the right. We know exactly where it's going to cross or touch the x-axis. We move on to step 3. Step 3 says to find the y-intercept. How did we find the y-intercept again? Plugging in 0. So we're doing f of 0, which is 0 to the 4th power minus 2 times 0 squared plus 1. What is f of 0? 1. Okay, easy. So we have a y-intercept at 1. Step 4 told me to check some symmetries. When we learned about symmetries in chapter 2, we learned that all you have to do is plug in negative x to the function and see what happens. So if I plug in a negative x everywhere there was an x and simplify, negative x to the 4th power is a negative times a negative times a negative times a negative. What is that? Positive. Then I'm going to do negative times negative, which again is positive, plus 1. Did anything change about this function? No, so it's called an even function, which means we are going to be symmetrical about the y-axis. So what happens on one side of the y-axis needs to happen on the other side of the y-axis. That's going to be our axis of symmetry. We do actually have one for this guy. Our last step, just to make sure we have everything where we need, is to look at the turning points. If our degree is 4, what's the maximum number of turning points I should have? It's actually below that. So the degree should be bigger than the turning points. The max number of turning points I have is 3, 1 less than that. That just gives us a place to check at the very end. Woo-wee! Feels like we've been working on this problem for a while. Let's actually start graphing. I feel like this music keeps getting louder, and I'm not changing the volume at all. Okay, let's plot some stuff. From the beginning, we know that the end behavior is rises on the right, rises on the left. So I'm going to go to the end of my graph, and I'm going to put a rises on the left, rises on the right. I know from step 2 that I have an x-intercept at -1 and at 1. And at both of those places, it's going to bounce, touch and turn, and go back up. Step 3 told me that I have a y-intercept at 1. Step 4 told me that I should be symmetrical across this y-axis. So if I do this and I plot all of these points, here's what it's going to look like. I hit the first x-intercept, I touch and turn. I hit the second x-intercept, I touch and turn. Is that function symmetrical across the y-axis? Does it have at most 1, 2, 3 turning points? We have graphed it successfully. Now I know that was a lot, and it takes a lot of effort to graph one of these kinds of functions, especially because this one had a really gnarly way to solve for the x-intercepts. This may be a lot easier on a lot of problems. We just happen to have one that required that use substitution. You've already seen one that required grouping. You saw one that required regular factoring with the GCF. This one required use sub. Just kind of depends on the kind of question that you have to find the solutions.